Okay, so as you're kind of finishing that there, I'm going to start chatting about this stuff. So on Friday, we were talking about linear regression, right? Linear means like a straight line. Now we're going to get into stuff with exponential stuff. Have you guys done exponential stuff before? Yeah, hopefully. So there's a different, so it's stuff with powers, but there's a difference between the exponential stuff and something like that, where it's like to the power of 2. This is actually quadratic, which is something we'll work on. It's, I don't know, one of the sections in this chapter. This is not like that, okay? These are variable, is going to be as the power instead of as the base, okay? So that's our exponential function there. It's based on multiplication instead of addition. So with our linear stuff, it was always going up or down by like a consistent rate. So like adding or subtracting a consistent number. Here instead, we're going to be multiplying by a consistent number instead. So instead of the add, it's just multiply instead. So that's our general function. The a can never equal 0 because if you took 0 times that stuff, you would just get 0, and that wouldn't really be helpful to us. Your b also has to be bigger than 0, so it can't be 0, and then it also can't be any of the negatives. It also can't be equal to 1 because if you put a 1 in there, what's 1 to the power of anything? 1, right? Because 1 times 1 times 1 times 1 times whatever is always still 1, right? So it can't be 1 either. The a in this formula is always going to be like your initial population of something, and then your b is going to be your growth factor, or what it's like changing by. The graphs in general look something like this, kind of like a ramp, where it's kind of flat on one side and then it's increasing pretty quickly on the other side. If it's going kind of to the right like this, that would be growth, where our b or our growth factor is bigger than 1. Going the other way, where our growth factor is between 1 and 0, like a decimal number, then it would be going the other way. To figure out what that a value is, if you don't know it, it's always the same as what our y-intercept is. So wherever it's crossing right there, that's always going to be our a value. Okay, another set of stuff to kind of write here. I'm also going to draw some little graphs here that kind of go with this. So if you want to make some little graphs, I'm going to draw some of that so you kind of know the difference between two of those things in there. They go with the range thing is what I'm going to draw them with. Okay, so let's take a look at this stuff. So these are just properties that go with those exponential functions. Your domain is always going to be all real numbers because it can go as far as it wants to the right and as far as it wants to the left and still be good. Your range is going to vary a little bit depending on if your A is bigger than 0 or smaller than 0, and that's what I wanted to draw the little picture of. So say I have, just going to do a little example here, say I have like y is equal to, let's go positive 1 times 2 and then x. So our A value is positive, so this would go with that one right there. Your graph is going to look something like that. Okay, so that's why it's positive real numbers, because it's going to be all of your values that are on top of that line. Okay, now your other one, this one looks a little bit goofy here. If it's a negative A value, so like if I go y is equal to, switch it to a negative 1, keep the 2 and the x, and I just made those up, but they don't really mean anything. But this one's a negative. What that actually ends up looking like, it's kind of like the graph is reflected over that x-axis. It actually is going to go down like that. Okay, so that's why that one is the negative real numbers, because it's on, for the range, because it's on the lower side of that. Okay, and then neither of those for the range are ever going to equal 0 because of the asymptotes. Do you guys remember asymptotes from Algebra 2? So asymptotes are basically your line that it's going to get really, really close to, but it's never actually going to touch. So it'll just get really, 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 really small or really big, depending on what you're doing. But yeah, it's never going to touch it. And that's kind of what that next thing is. If you didn't remember what that terminology was, it would be coming up really, really close to that line there, but it's never actually going to cross that line. Okay, and that will be true with all of this exponential stuff. Okay? All right. Next thing I believe is on our example sheet. Yeah, next thing's an example. So we'll switch to our little packets. Okay. So we got two towns here. We got Scarsdale and Ampleton. Both have approximately 8,500 residents. Over the next 5 years, the population of Ampleton is expected to increase by approximately 2.3%, and Scarsdale is expected to decrease by 0.9%. We're supposed to create equations to describe the population of each town as a function of time. Okay, so coming up with our equations here, we're following kind of that same formula, the y is equal to a times the b to the power of x. Remembering from our stuff we just wrote, A is always like our starting population, and B is our growth factor. Okay, so when we set these up, that thing wouldn't go out on me. There we go. When we set these up, let's go, since we're probably using x's and y's for both of them, let's make them functions, and let's make the one that's the A name, like A is the function of, and then what do they have for, we're trying to figure out, T for time in years. Let's go like that, make it a function so we can tell which one's which. Okay, so then our first thing here is always going to be like our initial population. So what's our population to start with? 8,500, right? So we're going to put that 8,500 in there, because that's true for both towns. Growth factor then is going to be what? Yeah, that point, or that 2.3, right? And we remember we got to turn that into a decimal, right? Another thing here is it's increasing by that, so we would want to actually take 100% plus what it's increasing by to get like what it would be after that 5 years. So it'd be like 102.3% is what we're using, and then we just go over, you know, 2 places, so that'd be like 1.023 as our number we put in there for the growth factor. You don't have to do that step, but it makes that step easier depending on what they kind of ask you. And then our power here is going to be what we're looking for, or one of the things we could be looking for, which would be that time. Okay, so then that's for our A town. Now we'll go with our S town, which is Scarsdale, starting with that same initial population, right, that 8,500. Now this time it's a decrease of 0.9. What do you think we would do for decrease? Yeah, minus it from that 100, right? So if we go the 100 minus that 0.9, we'd get 99.1, go over our 2 places to turn it into a decimal, so 0.991 as our percent there. And again, there's other ways to do that, but we'll go with this because that's what the book's got. Okay, so that's our setup there. And then for part B, it wants us to actually do some projected populations for 5 years down the road. So where's the 5 going to go into our formulas? For the T, right? Because that's what we're trying to find there, or we're trying to find what our population is going to be after that T amount of years. So we'll put that in there. So I'm going to start with the A1. So it'd be like A of 5, if we're doing it as functions, is equal to that 8,500 times 1.023 to the power of 5. And then I just plug that straight into my calculator. If you're following along with order of operations, you'd want to do that power first, and then once you get that number, take it times that number. Your calculator should, in this setup, do order of operations anyway, because it'll do the power and then it'll do the times. I'll just give you what I approximately got. I got approximately 9,523.5. I think it's a 5.7 I've got. It's either a 5.7 or a 5.1. 5.1 I think is actually what it is. Poor handwriting. And then what was that we were figuring out? If that was our time, what's this kick out? People, right? So people are like our population, or like residents, or people, or whatever. Okay, so that's for the one town. Other town, same thing, except for our percentage is different. So we'll go 0.991 in there instead, but still to the power of 5. And again, you do your power first and then do your multiply. For that one, I got approximately 8,124.32 residents. And since it is residents, you probably don't need those decimals on there, but I'm not going to worry too much about that. Okay, and then it wants us to compare those. Okay, what could we do to compare those populations?
Like, see how many percent more the bigger one is than the smaller one.
Okay, so we could figure out how much bigger the one is than the other, right? So if we could figure out like how much one went up compared to the other, right? Like if we did our like initial population, well, it would be this one minus the initial one, so like 9,523.51, or if you want to leave the 5.1 off, that'd be fine, minus our 8,500. We could do that to figure out how much it grew by. So that'd be, I calculated that to be 1,023.51. And then we could do the same thing with our other town, right? So if that one we did where we're at, the 1,124.32 minus where we started, to figure out the difference after 5 years, that one would be negative 375.86. Why is that one negative? It decreased, right? So we could put for this, what was the A town? Ampleton. We could put like Ampleton increased by about 1,023 residents or people, and then the other one went down by about that much. That'd be one thing we could compare. Scarce. I don't think I'm spelling that town right. Scarsdale decreased by about 370. I don't know if you want to round that up or down. The other one I didn't round, so we'll go like that. Something along those lines. Or you could round them up, make that a 4 and that a 6. That'd be fine too. As long as you're around that, because however you round it could be a little different. Okay, does that make sense? Basically just plug it in. Alright, back to our notes here. Okay, so one more thing to write, and then we'll have a couple examples. So you've probably seen this formula before, but if you don't remember it, there's the formula. Okay, so like I said, you've probably seen this compound interest formula before. I know we do it in like regular algebra, and it's probably mixed in algebra 2 stuff as well. So it's a pretty common one for calculating interest, usually with like bank accounts and that kind of thing. So your A is always going to stand for your account balance. P is your principal or your starting amount. R is always going to be your percent yield, or just like your percentage, or it's R because it's a rate. And then we're always going to make sure we want to turn that into a decimal. And then T is our time in years. So very similar to the other one. They just kind of mix in that. So you know how before we had that 100% and then we added it to like our 2.3 or whatever. They're just putting that in there that you have to add the 1 to it already instead of making us come up with that. But very common formula, so you're probably familiar with that. Okay, so back to our packets here. So they got Jonas received a letter from his credit union, which is kind of like a bank, stating that a 5-year CD his parents opened for him has matured, and he could choose one of the following options. He can either take it out of the bank and withdraw the full amount. He can use that money, so that 14,000 number, to open a new CD, so kind of roll it over into a new account. This time that account's going to be at 2.1 or 2.81%. Or he can take that money and deposit it into a checking account that earns 0.95% interest. Do you guys know the difference between a CD and a normal checking account or savings account? So CDs, they stand for certificate of deposit. Usually there's more rules with those. So usually you get a higher interest rate on it, so you're going to make more money from it than if you just put it in like a normal one. But there's rules that say, like, if it's a 5-year CD, you can't take that money out of that account for 5 years. Okay, so it has to stay in the bank. That's why you get a higher rate. But there's, like, if you did take it out early, there would be like a penalty for that, if that makes any sense. So it's good if you got money to invest, but if you need it in the short term, it's better in a checking account or a savings account. Anyways, so for A, it wants us to come up with, and we're supposed to assume Jonah's parents deposited $12,000 into a CD 5 years ago. I wish my parents would give me $12,000. That'd be awesome, but I don't think that's happening. So we're supposed to come up with an equation for the balance after 5 years. Okay, so we're just using that same equation we just wrote down, trying to figure out our, what are we trying to figure out? The interest rate is, I think, what we don't know from the old account, so not from the new account, but the old one. So we do know our account balance at that time after the first CD we did was that 14,204.10. And then we know that we started with that 12,000 number, so that would be our principal. Then we go percent, 1 plus. Our rate of our original account is what we don't know, so we're going to leave that as the R. And then we know it was a 5-year CD, so it was in there for 5 years. So the only thing we don't know is the interest rate, which conveniently is what we're trying to figure out for part B. So A is that setup. Now B is us actually solving for that annual yield or that percentage. So I'm going to just rewrite that same formula. So 14,204 and 10 cents is equal to my 12,000, and then parentheses 1 plus my R that I'm trying to find to the power 5. And if we need to solve for R, what do you think our first step is? It's a little bit tricky with that power in there. If this was just like x to the power of 2 and that was just multiply, what do you think? Yep. Yeah, that 1,200 or that 12,000, right? So we're going to divide by that 12,000 to get rid of it. And that'll be gone from that side, so we'll have 1 plus R to the power of 5, and then I think that is not a great number. I got like 1.18, I don't know, you just want to go like 3.7. It's kind of a rough number there. We'll just round it, just get an approximate. Okay, now the big question is, what do we do from here?
Take that and put the exponent as 1 divided by 5.
Yes, so we're going to do it as the 5th root. Okay, so like say we had something, say it was like x squared or something that we were trying to get by itself. The opposite of squaring something is square rooting it, right? So same works when it's to the power of 5. It would be, so like if we did 5th root of whatever that was, that would be the same as like what Weston said, to to the power of 1/5. So yeah, I would agree there. I would take everything there to the power of 1/5. Because that 5 and the 1/5 will cancel each other out. And then on that side, we'd just be left with, 1 plus r. And then we would just take this number here. If you left it in your calculator, that would be ideal, to the power of 1/5, which I got 1.034, something like that. I rounded a little different, so it might be a little bit off there. And then now to get rid of that 100%, to get it down to just our percent of change there for the yield, subtract that 1 from each side. So about 0.034 for our rate. You could probably put approximately equal to there as well, since we did do some rounding. And then we know if we need to turn that into a percentage, go over 2 places, right? So our R would be approximately 3.4%. Okay, and then part C, they want us to compare the results for option 2 and option 3. Okay, so option 2, so we're not using this equation anymore because this was for the old one. We're just making our own new ones. So it'd be like our account balance is equal to, this time we're using the 14,204.10 as our starting amount, because now we're talking about like what we're doing with our money after 5 years of it getting kicked out. And then option 2 would be 1 plus, what was our decimal on that one? 0.0281 to the power of 5. So if you do all the solving out for that, I got that account balance is approximately equal to $16,315.13. And then you just do the same thing with the second account there, or I guess it's option 3. Still, you're using that 14,000 number as our new starting amount, and then this time our decimal is 0.0095 to the power of 5. And then when I put that in my calculator, I got approximately 14,891. Of course, the thing goes out. 0.74. And then they just want you to compare those. Which of those is a better option? 2 or 3? 2 is a way better option, right? So I'll just do option 2 is way better, which seems kind of obvious because it's at a much higher percent, so I don't know why they asked that, but they do. Okay, let's stop there. We got one more example to do. We'll keep working on this tomorrow.